So we continue the previous lecture that took place 2 weeks ago, and it will be given a conventional title, the transcendental theorem theory of the moduli stack over complex numbers. The informal idea is as follows. As we have discussed, the difference between the moduli stack or fine moduli space and the coarse moduli space is in considering is that this object is this thing is generally not a set but rather a category, and instead of considering the set of classes of isomorphisms of curves, we consider family of curves. Therefore, going beyond the set theoretical mathematics. However, the same ideology oversee using some strong complex analytical tools keeps us within the set theory, and this is what I'm going to discuss now. Maybe we'll have the time to discuss something else as well. Okay, so we stopped at the constructions, or maybe started by the construction. Let's fix the genus as a natural number. This time we'll start with 1, though genus 1 is very special in this theory, however quite typical, very important to understand the whole theory. Well then, yes, perhaps I need some more general words. The theory I'm going to speak about now is by no means categorical or functorial, but only in one respect. The best understanding of it is gained by fixing some initial point of the theory. So we fix it and we fix, so say x naught. How do we, well, let's just remind ourselves that there exists a coarse modular space. I mean, in these notations we make no distinctions between the curve and its isomorphic class. So this curve is really arbitrary, but should be fixed. And in fact, I have some non-standard suggestion that is compatible with other theories close to the ones we are discussing. So I'd write maybe the affine model of x naught will be y square equals 1 minus x to 2j plus 1. It is a somewhat arbitrary choice. However, in some cases, these, as you see, it's the x branch. It is the Fermat curve of special kind, and its branch points are somewhat mostly symmetric. Obviously, lies in the root of, well, obviously, right, are roots of 1 and 0 and infinity. Well, one of the reasons is that the uniformization, the complex uniformization of these curves can be written down quite explicitly, and it is one of the few curves like that, having, well, the shortest possible equation. But we'll never use it and think about x naught as about an arbitrary marked point. And well, as for the functoriality of the theory, it is something like, well, instead of forgetting the theory, instead of considering the functors, curves over C to its topological model. Sorry, we denote functors like this. Forget. We consider various complex structures on the fixed curve. Structures on x naught, various, or in other words, consider deformations. Deformations on the fixed structure. So theoretically, we change our point of view and just think about the single curve on which we are going to consider various structures. And as we did before, without emphasizing that what we are going to consider is the space of all metrics over x naught. We have discussed it from the general point of classification of structures, and inside it we consider the set of Riemannian metrics. Well, I think we write this not all the time, all the way, and perhaps now I erase everything and maybe forget about this choice. Well, I have to remind the purely group theoretical, set theoretical, group theoretical structure. So on the Riemann surface, on the set of Riemannian matrix, we have the action of two groups. First, write them separately. It is C infinity. Oh, sorry, not here. C infinity. Or, well, I'm not really sure whether I should write. Oh, yes, I will. C infinity. It acts in the obvious way for the phi belonging to being a smooth function of x. Not? Well, we mean, without marking complex number, we mean real function. Then phi applied to a Riemann structure like this is just by definition the exponent applied to it pointwise. So this is one of them, and the other is the diffeomorphism group. Plus of x 0, and it was claimed that is rather some lectures ago, and it is rather easy to check that these actions do not commute. However, since the diffeomorphisms act on the group of functions in the obvious way, then the whole action of this semi-direct product is defined, and it was claimed. While I don't mean at all that the fact is obvious, it is, well, let me mark it as a classical one, but this identity, well, set theoretical identity, is a result of several basic theorems of 19th century, like uniformization, the only metric of constant curvature on surface, and so on. So it is not at all easy. Well, the right hand side is like this. As you see, it does not contain this non-canonical isomorphism is also rather conventional, because first of all it has no reference to the fixed points, to the distinguished curve, and secondly we know that this object is a quasi-projective, at least algebraic variety, while this one is carries. By the way, perhaps let's decide that it carries no structure at all, because literally it is a factor of something terribly infinite dimensional, over an infinite dimensional group. But the first trick to, in fact we'll see an almost complex structure in it, because being wildly infinite dimensional and in many texts demanding the formalisms of Fréchet manifolds, Banach spaces and so on, we'll avoid all this, because it will turn out very soon that we are able to linearize this object. So we'll find soon that the action of this group has the orbits have finite codimension, and we'll write down explicitly the linear factor, so the tangent space to this. But as for this, not this distinguished point, it just means that this set is has an interpretation as was declared recently of various complex structures on the fixed curve, or better, from now on we say Riemann surface instead, because we are going to use analytical tool. So one of the tricks is to start with the action of this group. So maybe the first part is to give an interpretation of Riemannian metrics on X naught over the group, has a meaning of conformal, so-called conformal metrics. By the way, the similar construction of course exists in any dimension, but dimension 2 is quite special, because in dimension 1 one checks easily that this factor is trivial, it's just a point. In dimensions 3 and 4 we do not consider the arbitrary metrics, and similar constructions are valid, but using in dimension 4, for example, one considers the Einstein metrics only. And then there are quite interesting finite dimension moduli spaces, though not any 4 manifolds admit Einstein metrics. So here we use a very special property of real dimension 2 in which we work. So we give the interpretation on it of conformal metrics in 2 ways. One was formulated on at the end of the previous lecture, that is almost complex structures. So I draw both, remind ourselves that what is important here is that the surfaces, when we forget forget algebraic structure, but remember the complex analytic structure, we have a distinguished orientation. Maybe I write it down oriented by and by any surface so say minus I, in any local metric we can demand this kind of orientation. So when we write down, so there are exactly two vectors of the same length orthogonal to D, but using orientation we select one of them, and then we get the then we fix the conformal metric just by one operator. So J X in any tangent space with the square minus this is one of the ways to fix conformal metric, and then we have a very nice definition of the action of the other group. So we have realized the factorization over the additive group of functions. Perhaps I better put plus here, meaning that it is not a ring but an additive group of it. And then we have to factorize the set of almost complex structures over another group. And so for phi being in fact any diffeomorphism without plus phi over applied to the almost complex structure J is by definition just phi composed with J with phi lower star, phi lower star inverse. Obviously this moves the point to another one, to phi inverse of this point, then we rotate it and then put back, and obviously this is still an almost complex structure. It is a nice problem that I am perhaps unable to solve without the technique I'm going to introduce now. As you see, we have a perfectly real analytic object, set of almost complex structures. By the way, it sits in some infinite dimensional linear space, yes, in the space of endomorphisms of the tangent bundle, and we factorize it over the infinite dimensional group. So the fact is that this action has the orbits of finite codimension. Sorry, I'm not sure how to give it an exact, how to give the statement an exact meaning, but we'll see very soon that, but we can already ask about the infinitesimal version of it, because the tangent space, the Lie algebra of the group of diffeomorphisms is just the Lie algebra of vector fields. So the Lie algebra acts on some subset of linear space. So but very soon we'll have this factor explicitly. So as I said, this is one way. Now I erase almost everything. And the second way is maybe not so obvious, but uses the complex structure. So as we can draw something like this x naught. Well, the complex structure is just the same as take any tangent space, and there are round. Since it is not a true metric but a conformal one, the circles in the tangent balls, tangent planes are not defined, but the sets of concentric circles are defined very well. Just the multiplication by a function just acts as the similarity on this picture. And then we introduce the deformed these structures, like let's just draw it. Maybe again draw this and draw something like that in the deformed vector structure. We still have some sets of real curves, and I think it is profitable to imagine them in the same tangent planes. So there are around the sets of round circles and another family of surface that we define by as the conformal factors like A. So suppose we are in some chart. I have no place to draw it, but the Riemann surface is covered by complex coordinates charts, and these circles are defined in the following way. Well, I write the formula in the cotangent space. So d z sub alpha plus mu sub alpha d z sub alpha bar square. Yes, is really proportional over R to the Riemannian tensor. So this is the main object. So a very simple exercise tells us, well, the absolute value of it is not defined yet now, yes. So the whole metric is defined up to the scalar factor, and we ignore it or put it here, and the conformal part is represented by this object that is called a Beltrami differential. And it is a tensor of rather special kind that we are going to introduce now. So perhaps we decide that everything is clear about the almost complex structures there. It is a nice exercise to relate these two ways of deforming the original structure, but it lies rather far from our course. Has maybe nothing to do with Grothendieck topology. Well, maybe there is some analog of all this. Now let us introduce something like perhaps tensor spaces. Tensor what? Tensor bundles, perhaps. Tensor bundles. T, M, N double indexed, M, X, not over X, not with the rule of substitution when we have it in Z sub alpha and Z sub beta. So they are transformed like U beta, say, well, I would say that the expressions like, well, the letter is T, say T sub alpha, D, Z sub alpha, 2 nth, D, Z sub beta, bar, 2 nth, where T sub alpha is the smooth function on the intersection of the charts and complex valued. Unlike what we meant here, it is complex valued. So is, let me write it a bit informally, alpha to beta invariant, alpha beta invariant, and rewrite it. It means that on the intersection on U sub alpha beta, say T beta is, so the coefficient is let's write it like this, Z sub alpha, no, just like this, D Z sub beta. It is just a holomorphic function. These bundles make sense only on the complex values. So these are to the degree either m or n. Let me see T beta S to m. So the relations are, neighborhood relations are holomorphic, so there are no differentiation over bar, but there is a bar of the whole derivative. So this is like this. This is the definition of these kind of tensor bundles. Now, just to recognize some, so T sub alpha, D Z alpha correspond to, well, 1, 0 forms, and then say T sub alpha D over D Z sub alpha, say bar correspond to 0 minus 1 forms, tensors forms, and so on. So Beltrami, now one checks that. Don't like to erase this picture, it is the most important, but I have to erase something. Well, suppose we erase this. And all these generalities are clear enough. Yes, I should admit that in my student times it was very difficult for me to follow these notations just because I never knew which functions were real valued, which complex valued, which structures were fixed or no. Yes. And in fact I was I was puzzled by the expressions that you'll find in any text like this. Without an index, I'll write just the word Beltrami. It corresponded to the expression mu d z bar over d z. That just made me faint. I didn't understand how you can take a dz bar and divide over dz. But it means exactly what is said here. Perhaps instead of this, let's write it down in a more realistic form. dz alpha bar over dz alpha. It is a bit longer, but I hope completely clear. So this is kind of quantities related to the conformal class of metrics. Well, maybe rewrite it. Maybe I rewrite it in other words. So, well, of course, I mean here u sub alpha, and here I mean u sub beta. And here is how they behave on the intersection. And just rewrite it once in a bit more compact form. It will say us that instead we put, just to be 100% sure, may I rewrite this as dz alpha over dz beta, and then the same thing over dz beta bar inverse. And it is nothing like, note that this is a non-zero function everywhere, and it is just the argument of dz alpha over dz beta square, yes? When I mean that for the complex number z is absolute value of E is the argument. So this is quite a funny, it is a complex bundle. It is, its fibers are complex one-dimensional spaces. But of course it is not a complex number because